So let's see the DFT as a linear transformation. So DFT or IDFT. So what is DFT? Let's say take the pen. So DFT I can say is x of k is equal to you know n equal to 0 to n minus 1 x of n w n n k, where w n is equal to e to the power minus j 2 pi by n. So I can say that if it is n point, let's say 8 point, so I can say w8 is equal to e to the power minus j 2 pi by 8. Okay or not? So I can calculate w8 easily. Then I can calculate, instead of calculating directly here, I can calculate w8 0, w8 1, because it is w8. So if the 8 point DFT, then w8 nk, or if I write, so it is nothing but a matrix. Wn is nothing but a matrix. Okay, xn is also a matrix and x of k is also a matrix. So let's say, what is x of k matrix? This is nothing but a x of 0, x of 1, x of 2, x of n minus 1. What is xn? X of n is also a signal. So I can say x of n, this is x of k. X of n is equal to nothing but a x0 matrix form, x1, x2, x of n minus 1. Okay. Now what is Wn matrix? So Wn is nothing but a, I can say, so Wn 0. When I say k equal to 0, if I put k equal to 0, Wn to the power 0 is nothing but a 1. So I can say upper matrix is 1, 1, 1, 1. How much? Wn n minus 1 times 0. Similarly, this side also I get, so this side I can get Wn nk. Okay, understand? Wn to the power nk. You can say there is a nk index. If I say this is j, this is k. So k index and n index. So if the n index is 0, when I say the n index is 0, then also Wn equal to 0. When the k index is Wn equal to 1, when is kn equal to 0, k equal to 0, then also it is 1. So I have a matrix which is a direction n cross k. So I can say, so all n also varies up to 0 to n minus 1 and k also varies from 0 to n minus 1. So this side also I have an n minus 1 element and this side also I have an n minus element. So if I want to write down Wn matrix, this side I have an 1, 1, 1, 1, 1, n minus 1 number of element. And this side, first column will be 1, n minus 1 number of 1. Second column will be Wn square, Wn cube, Wn to the power n minus 1. Okay? Okay or not? Similarly, Wn square, if it is Wn square, sorry, W first is Wn, then square, then n minus 1. Similarly, Wn Wn square, Wn cube, dot 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 dot, Wn n minus 1. So I have an n cross n matrix of Wn, which varies from 0 to n minus 1. Now I can say what is DFT. Discrete Fourier transform is nothing but a x of k is equal to summation of n equal to 0 to n minus 1 x of n Wn nk. So I can say it is nothing but a x of n multiplied by, I can say Wn multiplied by x of n. So I can say x of k is nothing but a Wn multiplied by x of n. So Wn is this matrix, coefficient matrix. Okay. Then if that, let's say I have a Wn has exist an inverse transform. So I can say x of n is equal to Wn inverse x of k. Linear transformation. So if Wn matrix exists its inverse transformation, then I can say x of n is nothing but a x of k divided by Wn, which is nothing but a matrix inverse. So this is nothing but a IDFT. Okay or not? But this Wn inverse is not exactly inverse of this Wn. What is Wn inverse? Basically the Wn inverse can be written as 1 by n Wn conjugate. Wn conjugate. So that's why Wn into Wn conjugate, if I say, is equal to W, or I can say this is nothing but a n into In, identity matrix. N into In. Okay. Let's an example, and then you understand how this kind of things will be, we can use for matrix algebra, can be used for calculation. So I have a signal x of n again. Let's say I have a signal, let's say 0, 1, 2, minus 3, 4 sample signal, and n is equal to 4. So I can say I have a W4 n k. So if I want to calculate the matrix, so 1, 1, 1, 1. This side 1, 1, 1. Okay. Now what is Wn nk? Let's say Wn into nk. N equal to 1, so what is first say? K equal to 1 and n equal to 1. So k equal to 1, n equal to 1, 1 into 1. Then I can say k equal to 1, n equal to 2. So 1 into 2. So what is Wn 1 into 1? Nothing but a Wn to the power 1. So what is the value? I can say Wn is equal to nothing but a e to the power minus j 2 pi by n, which is nothing but a e to the power minus j 2 pi by 4 in this case. So I can say it is nothing but a minus j. So I can say minus j to the power 1. So here it will be minus j to the power 1 minus j to the power 1 into 2 and minus j to the power 1 into 3. Okay. So it is nothing but I can say, simplify it, minus j to the power 1 minus j whole square is nothing but a minus 1. So, this will be replaced by minus 1 and this will be replaced by j. So, the matrix is W4, Wn or W4 matrix will come 1, 1, 1, 1, 1, 1, 1. So, it is minus j, minus 1, j. Then it will come again, if you calculate, it will come minus 1, 1 and minus 1, and then it will come j minus 1 minus. This is the W4 matrix. You can calculate, you can do it. Now, if I multiply this with, so x of k matrix is nothing but this Wn matrix multiplied by signal matrix x of n. So, what is signal matrix? So, I can say it is 1, 1, 1. So, I can say 1, 1, 1, 1, 1, 1, 1 and minus j, minus 1 j, minus j, minus 1 j, minus 1, 1, minus 1, minus 1, 1, minus 1 and j minus 1 minus j, j minus 1 minus j. This multiply by x equal to 0. So, x equal to 0 is 0, x equal to 1 is 1, 2 and minus 3, 1, 2 and minus 3. Now, you do the multiplication. So, you can get x of k. So, x of, you get x of 0, x of 1, x of 2, x of 3. You get that. So, by linear transformation also I can calculate the discrete Fourier transform DFT. This is the calculation. So, how do, suppose you want to implement it, forget about that hands calculation. Let's say I give you a signal whose length is equal to 160 sample and I told you, let's say given practical example, I told you record a acoustic signal or audio signal and collect 160 sample and compute, let's say 256 point DFT. So, I collected 160 samples. So, my x of n is varies from 0 to 159 number of samples. I have to compute n equal to 256 point DFT to get x of k. So, x of k consists of 0 to 255 values. So, how do I do it? First, I have to write a program of the DFT. So, what is the program? Very simple. So, I know what is the program of the DFT program. Let us say take another slide. Simple maths, let us say without any simplification of complexity and other things. I just simply I want to implement DFT in a C function. Implement DFT in a C function. So, I said write a C algorithm for computing DFT, discrete Fourier transform. So, you know x of k is equal to n equal to 0 to n minus 1 x of n into e to the power minus j 2 pi by n into nk. So, instead of every time I calculating this one, so if it is 256, so I can calculate j 2 pi by 256. That coefficient I can calculate separately, which is nothing but a cos 2 pi by 256 minus j sin 2 pi by 256. So, I can calculate this Wn matrix and store in a file. Now, I simply multiply xn with that things and write a for loop, multiply that and add them. or you can directly also do it. So instead, so mathematics is nothing but a n equal to 0 to n minus 1 x of n into cos 2 pi by 256 into nk minus j sin 2 pi by 256 nk. So you have a very for loop, first k equal to first for loop k from 0 to n minus 1, second for loop will calculate it for every k which will vary from 0 to n minus 1. So I have a nested for loop, first for loop for k and second for loop for n. For every k I have to calculate all n product and sum. So I can easily write down that thing, the for program. Okay. So this is the, you can say that calculation of DFT. Then that how do now if I say, if I ask you 160 sample 256 point DFT, plot the magnitude spectra, draw the magnitude spectra for practical application. Let's say I said record your voice, you create record the voice. From that voice you take a window of the voice. I am not, other part I am not explaining, that part I will explain later on STFT. So you take a window of the voice and collect 160 sample, or I said, let's say practically I said record a vowel let's say for 1 second with a sampling frequency fs is equal to 16 kilohertz. So how many sample in 1 second will be there? 16 into 10 to the power 3 sample will be there. Let's say take a 20 millisecond window at the middle, 20 millisecond signal from the middle. So you create, mark the middle, 10 millisecond this side, 10 millisecond this side. So what are the sample index? So here 16 into 10 to the power 3 sample is there. So half of that means 8 into 10 to the power 3. So I go to that sample. And then I said take 20 milliseconds. So how many sample will be there in 20 milliseconds? So 20 millisecond, in 1 second I have 16 into 10 to the power 3 sample. So in 1 millisecond, that many sample, in 20 millisecond multiply by 20. So 320 sample. So 10 millisecond divided by 2, 160 sample. Okay. So this side 160 sample and this side 160 sample I have. So I have an x of n which has 320 sample. Okay. Now I said compute DFT with length of the DFT n equal to 512 point. So how many 0 I have to pad up? M is equal to 320 and n is equal to 512. So I have to 320, I have to make 512. So that many 0 I have to added. So outside the window my signal will be 0. Now I write the C program and compute the DFT. So once I compute the DFT, I get x of k. So x of k has a value 0th sample. So x of 0 to x of 511. So that many x value will be there, and every x is a complex number. So I have to calculate mod of x0, mod of x1, mod of x2. I can calculate easily. You calculate it. So you get a sequence which is mod of xk. Now I told you, plot the magnitude spectra. So magnitude spectra means x axis will be k and y-axis will be mod of xk. So I have already computed different xk value and I have taken the mod. I just plot that value. So you can get this kind of plot. Let's say this kind of plot you get. Here k equal to 512, k equal to 511. Last point, k equal to 0. You can see you get a symmetrical plot at k equal to n by 2. So this portion will be look like same this portion. Why? You have seen that n is equal to 2 pi. So I have divided the 2 pi frequency in a n number of sample, which is 512. So n by 2 is nothing but a pi. I know the baseband signal frequency can vary from 0 to pi or 0 to minus pi. That's why I get 0 to pi and this represents 0 to minus pi. You can fold this side, so that's why this is 2 pi. You can plot and see it. Using MATLAB or using C program, you can plot it, calculate the value, go to the Excel sheet and plot that Excel, or you can use other plot function also. You can see this kind of plot you will get. Now, let's say in an ideal case, if I say that, okay, let's take another slide. Write down the problem. Generate a signal x of n which has a frequency component 200 Hz and 1.2 kilohertz with a sampling frequency 8 kilohertz. I said first you write a program to generate a signal xn which has a two component 200 Hz with amplitude 10 and 1.2 kilohertz, let's say amplitude 20. So what is the equation? X of n is equal to 10 cosine wave, let's say cos function, cos 2 pi 200 Hz f by fs 8 kilohertz plus 20 cos 2 pi into 1.2 kilohertz divided by 8 kilohertz. So this is your xn. So generate 1000 samples. How do you generate? You write a for loop for n equal to 0 to 1000 minus 1, so 999, okay, n minus 1, x of n, compute this one, you can write this function here directly, okay. So now x of n has an array which contain the 1000 sample of this signal. Now I said compute DFT of length n equal to 1000. Compute the DFT of length n equal to 1000. So zero padding is not required. I generate it. Now you compute. So what I get? I get x of k. 1000 sample of x of k. Now I said draw the magnitude spectra of x of k. So draw the magnitude spectra. So I draw it. How do I draw it? I put it k in this axis and this axis is mod of xk. Now I told you instead of discrete frequency, draw it against the analog frequency scale, Hertz scale. So I want convert this to, this axis is Hertz and this axis is mod of xk. So how do you convert? K equal to 0 means f equal to 0. So this scale is f. k equal to 0 means f also 0. K equal to 1 means f equal to how much? F equal to 2 pi by n into k. So k equal to 1. So it is nothing but a 2 pi. What is the 2 pi? 2 pi means 8 kilohertz. Sampling frequency is 8 kilohertz. So 8 divided by n equal to 1000. So resolution is 8 hertz. So I got 8 hertz, 16 hertz, 24 hertz, 32 hertz. So those points I will get. Now if I want to generate 200 hertz, what should be the k value? So resolution is 8 hertz. So k is equal to 200 divided by the resolution. So I can say it is nothing but a 2, 16, 25. So I get k at k equal to 25, I get 200 hertz component. Okay, and then 1.2 kilohertz. So 1.2 kilohertz divided by 8. So I know at k equal to 150, I get 1.2 kilohertz component. Now suppose instead of 200 hertz, let's say 150 hertz. Then what is the value of k? K equal to 150 divided by 8. So I can say 1 18 point something is coming. So k is come in fraction. So either k equal to 18 or k equal to 19, because k cannot be fraction. So in F case, so either I get 8 into 18, which is equal to 144, or I get 8 into 19. (152). So either 152 hertz or get 144 hertz. So I cannot get exactly 150 hertz. So as you know, what should be the look like? The ideal spectra should be very high spike at particular frequency, and rest where it will be 0. But if you draw it, you get not high spike, you get this kind of distribution, which is called DFT leakage. DFT leakage, because the power of the 150 hertz component will be distributed nearby, and also, so once you are, since your frequency resolution is 8 hertz, your frequency resolution is 8 hertz, so you can say that it is nothing but up to 8 hertz the information is same. So you can get an sync function kind of response. So instead of for idle to 150 hertz component, what is the idle frequency response? At 150 hertz it will be very sharp spike, otherwise it will be 0. But once you draw it, you cannot get that idle one. You can get that energy is distributed to nearby component also. So that is called DFT leakage. You do it and see it, and you feel what is DFT leakage. Now if you decrease the resolution, you see that power is distributed among nearby lines. So if you increase the resolution, you see the peak is coming very sharp, means leakage is reduced. Suppose if I want to make the resolution 1 hertz in this case, then what should be the length of the DFT? 8000, which is computationally very complex. So that is depending on your requirement, you have to choose the DFT length. That I will come, that how it is make it computational effective, which is called effective fast Fourier transform. So fast Fourier transform will explain how it is done and how it is improved the speed of the calculation of the DFT, and then we express the properties of DFT. So different properties are there. So zero padding I have already mentioned. I have mentioned the DFT leakage. I have mentioned the symmetry. So mathematically we see what is symmetry property, circular convolution. So those things will come in the next lecture. Okay. Thank you.